Let's look at these quadratic inequalities. Whenever you graph quadratic inequalities, sometimes the quadratic will be presented in standard form and sometimes it'll be in vertex form. And as we talked about, those give you different things immediately, and there's certain things that you have to solve for. Anytime you graph a solid curve, you use, just like in any inequalities, for solid, you use for greater than and equal and less than and equal, it's solid. And for just greater or just less, you use dashed. We'll use test points for these, just like we did for linear inequalities. And you can pick any point that isn't on the curve. You'll substitute into the inequality and make sure that it's true, that it tests true. If the point is true, then you shade the area that contains the point. And if the point is false for the inequality, then you shade not that area. You shade in the other space. It'll either be inside the curve or outside the curve. We'll describe the areas that have solutions using the quadrants. And you count the quadrants in counterclockwise order, starting where X and Y are both positive. So you can draw a C around the origin to mark how you count the quadrants, if that helps you. Also, we use Roman numerals to name the quadrants, not Arabic numbers. Whenever you're describing where the solutions are, assume that you zoom out as much as you can and you can see the whole big giantest graph there ever was. And that's how you'll answer what quadrants contain solutions. So it may not be just what you see on the graph on the square that you are drawing on. Because we're going to assume an infinitely large graph, there are always at least two quadrants that contain solutions, and that's because if it's inside the curve and the curve is showing only in one quadrant, eventually it will get wide enough, if you get far enough out from the origin, that it will also go into the quadrant beside it. So there's always at least two quadrants that contain solutions. These are examples of what quadratic inequalities look like. Both of these are greater than. Notice both of the boundaries are dashed. It's been a common confusion to have people try to create rules for themselves to know where to shade. I want to kind of save you from yourself for that. Both of these are greater than. One of them is inside the curve. One of them is outside the curve. So I've had people come to me like before a test and say, so if it's greater than, it's inside the curve, and if it's less than, it's outside the curve, right? And I say, well, no, it depends on the graph. It depends on the inequality. So don't get into some kind of a trap like that you're trying to create a rule. Instead, we'll use a test point. I want you to use a test point even if you feel strongly that you know exactly where to shade it. And the reason is you may have graphed your inequality wrong. So pick a point that's not on the curve. And if your test point solution is a complete surprise, then make sure that you graphed the right quadratic. Make sure the parabola is correct. For both of these, you'll notice though that they're greater than, and the solution is greater than the vertex. So greater than the vertex could be inside or it could be outside the curve. And that will stand true. If it's less than, it will be less than the vertex, whether that's inside the curve or outside the curve. But again, we're going to use a test point anyway. I have two examples for you. The first one is written in vertex form. Vertex form is when it's an equation, it has a, h, and k in it. So it's y equals a parentheses x minus h squared plus k. And it's called vertex form because the vertex is hk. We need to identify what a and h and k are, because for a vertex equation or vertex inequality, that's going to help us a lot with graphing. So for this inequality, a is 2 and h is -1. And the reason for h being -1 is originally the middle of the equation is x minus h. I have parentheses x plus 1 in the middle of this, and this is written this way as like short, it's not a shortcut, but it's because it's kind of awkward to write x minus -1. But that's why h is negative, is because the middle should be an x minus expression. K is the number that's at the end, so that's also -1. Since hk is the vertex, when it asks for the vertex right below this, I would say that it's -1, -1. And we can plot that point. Go ahead and plot that. The axis of symmetry is a vertical line that goes through the vertex and splits the quadratic graph in half. We'll go ahead and draw that line as well. And the y changes all along this line, but the x remains constant. So the equation for the axis of symmetry is x equals -1. Make sure that when you describe the axis of symmetry, that it's an equation. It should have a variable and an equal sign. For equations and inequalities written in this form, it's not obvious just from looking at the equation what the y-intercept is, but we know that the y-intercept on the y-axis is where x equals 0. So I know the x part of the point. And again, this is because x equals 0 on the y-axis. So I'll substitute 0 for x in the inequality that I'm given. Since I'm solving for an exact point, and I'm not shading answers, when I solve this, I'm going to solve the equation. So even though we're graphing an inequality for this, I'm going to write y equals 2 times 0, that's my x, plus 1. The 0 plus 1 is squared, and then there's a negative or a -1 after. Zero plus 1 is 0. No, it isn't. 0 plus 1 is 1. And 1 squared is 1. So I get 2 times 1 minus 1. 2 times 1 is 2, minus 1 is 1. So y equals 1 when x is 0. So I can put 0, 1 as my y-intercept. And you can graph that point as well. Okay. So I have 2 points. Let's do a calculation. We'll do the same as what we just did to find the y-intercept, but I'll substitute x equals 1. I want to find another point on the same side. I'm already drawing my curve to the right. So let's choose x equals 1. We'll substitute for x and solve for y. Go ahead and do that. So I'm substituting 1 for x this time. And this is arbitrary. I could choose 2 or 5 or 18 or whatever. I want to make sure that the point fits on the graph so that it's useful for me. And you do the parentheses first. So 1 plus 1 is 2. And I square that, so I get 4. So y is going to be equal to 2 times 4 minus 1. 2 times 4 is 8. 8 minus 1 is 7. So I find that when x is 1, y is 7. And you can plot that point. Well, with a little imagination, you can plot that point. It doesn't fit exactly on this graph. Oh, yes, it does. Okay, 1, 7. So here's my extra point. And then I can draw in my curve. When I draw this in, since it's an inequality, and I have y less than, I'll draw in a dashed curve because there's no equals with my inequality symbol. So when you draw this half of the curve, make a dashed boundary, which looks like this. So this is half. And then I already drew my axis of symmetry on here. I can reflect these points, this curve, over the axis of symmetry, and that gives me the rest of the parabola here. All right, now I need to shade where my solutions are. So I'll pick a test point, any point that's not on the curve. I pick 0, 0 a lot of the time. Or I pick a number that will make a 0 somewhere in my equation, but you can, honestly, you can pick any point. What point would you like to test? Just nothing on the curve. Somebody. Nobody has a vote? Pick a point. That's not 1, negative 1. Nope. Oh, 1, negative 1. Yes. Okay. So we're going to test here. There. We'll test 1, negative 1. That's 0, negative 1. How am I doing? It's that day? There. 1, negative 1. So to test a point, you substitute the x and the y into the inequality, and we're just trying to see if this is true, if the inequality is true. So I want to know for 1, negative 1 is negative 1, this is the y, less than 2 times 1 plus 1 squared minus 1. So I simplify the part on the right, parentheses first. So I get 2 squared. So I'm calculating 2 times 4 minus 1. This is 5. Is negative 1 less than 5? Yeah. Since my test point tests true, I shade the part of the graph where the negative 1 is.
How did you get 5? Yeah.
Oh, because it's Monday where I am. Thanks for asking. 2 times 4 is 8. 8 minus 1 is 7. Wow. I'm glad you're awake, Z. What? It's not 7 either? I'm crying. Okay. Yes, this is true. So shade where negative 1 is. All right. My solutions are everywhere on the same side of the curve. Oh, which is the outside the curve. Just a moment. My solutions are everywhere outside the curve, just like negative 1 is outside the curve, and that tested true. Questions right now? Okay, the other example that I have is written in standard form. For standard form, I have y is ax squared plus bx plus c. So for this inequality, I will identify a, b, and c. A is 2. B is 12. C is 21. For a standard form inequality, it's not obvious what the vertex is. It's not obvious what the axis of symmetry is. We'll have to calculate those. What's really easy to read off of a graph that, or an equation or inequality that's in standard form is what's the y-intercept. So that's what we're asked first, because it'll be 0c, and you don't have to memorize that, but we know that x equals 0 on the y-axis. So if I substitute 0 into this inequality, we're calculating a point, so I'm going to use it like it's an equation. I'll pretend it's an equation. Set it up to substitute. And plus 21, where the spaces are, I'll write my x, and I'm choosing that x is 0. When I do 2 times 0 squared, I get 0. And 12 times 0 is 0. So when x is 0, y is 21. That's the c. So there's a point 0, 21 on this graph. It's way up here, not on your, I'm going to put a little broken line and then continuing up. 0, 21 is not on this box. It's way up there. But this should help us once we figure out what our vertex is to know if it's opening up or down. Okay. Axis of symmetry is a calculation when you have a standard form equation or inequality. My axis of symmetry is always this formula, x equals negative, and you substitute the b value divided by 2 times whatever the a value is. For this graph we're trying to draw, b is 12 and a is 2. So to find the axis of symmetry, we'll substitute this will be opposite sign 12 divided by 2 times 2. So I have negative 12 over 4. The axis of symmetry is an equation of a line. So I'm not just going to write negative 3. I'm going to write x equals negative 3. This is my axis of symmetry. Go ahead and draw that on your graph. So regardless of what the y is, x remains constant. It's always negative 3. It's a vertical line. My vertex will be on this line. The axis of symmetry goes through the vertex. So now I know what the x is for the vertex. X is going to be negative 3. I don't know what the y is. I'll have to calculate that. So this is going to be y equals 2 times negative 3 squared plus 12 times negative 3 plus 21. I put negative 3 in place of x. Negative 3 squared is 9. Negative 3 times negative 3. I have 2 times 9. So this starts out with 18. 2 times 9, and then 12 times negative 3 is negative 36 plus 21. 18 minus 36 is negative 18 plus 21 is 3. So when x is negative 3, y is 3. And you are, invited to use the calculator too. That's fine, if that's your thing. So negative 3, 3 is on this axis of symmetry, and I'll draw that as my vertex.
How do we get the last numbers?
I calculated them.
How do you do that?
You multiply and add. Yeah. Thanks for the question. So here's my vertex, and I know that it opens up because there's a point over here way up high on my axis of symmetry. You also know it opens up because a is a positive number. But I need to find some points that will fit on this graph so that I can draw my curve in. We calculated last time. You can do that now. You could put in negative 2 for x or negative 1 for x. I know that when x is 0, it doesn't fit on my graph. Or you can use the step pattern that I explained. The step pattern is from wherever my vertex is, I would go right 1 block, and then I would go up or down a times 1. Let's say it's up. It'll be up for this one. So then I would go right 1 block again, and I would go up or down a times 3. And then I would go right 1 block again, and I would go up or down a times 5. And you continue multiplying by odd numbers, 1, 3, 5, 7, 9, 11, 13. Since a is 2 for this inequality we're graphing, I would go from this vertex where I am, I would go right 1 and up a times 1. So 2 times 1, I would go up 2. And then from that block, I would go right 1 and up 2 times 3. So up 6. 1, 2, 3, 4, 5. It barely doesn't fit on here. It's just above. It would be at negative 111. When I draw this curve in, will it be solid or dashed? It is solid. Why? because it has an equal to with it, yes. So I'll draw this curve in, half of the curve, solid, just like I would if it was an equation. This is reflected over my axis of symmetry, so I can draw a point that's also at y is 5, and I can draw another point which is also when y is 11, and draw in the rest of my curve. Since this is not an equation, I'll have to shade my solutions. I did a test point and it was true. I'm going to do a test point that's false. So let's pick 0, 0. Greater than, y is greater than, so your solutions are greater than, it should be inside this. That would be greater than the vertex, but we're testing anyway. 0, 0. We said this was solid. Actually, let's test a point that's really close, so that kind of like what Ethan chose. So that then if my graph was wonky, I could tell very soon that my graph was wrong. Let's test here, -3, 1. That way, if my graph is actually drawn upside down, I could catch myself. So we're going to test -3, 1 and the inequality that we're graphing. So I'll write is 1 greater than or equal to 2 times -3 squared plus 12 times -3 plus 21. Well, left side is really, there's nothing to do over there, but we can simplify the right. -3 times -3 is 9, so I got 2 times 9, and then, oh, we already solved this. We already calculated the right side because we used x is -3 up here. We got this is 3. Is 1 greater than or equal to 3? No. You see what I'm referring to? We just did this calculation up here where x is -3, but I chose a different y. So I already know it's 3. 1 is not greater than or equal to 3, so you don't shade on that side. The other side of the curve. -3, 1 is outside the curve, and that was false. So my solutions are inside the curve. Is that reasonable? So my solutions are in here. Everything on the inside. Also, any number on that curve. And we describe our solutions as the quadrants which contain shaded areas in an infinitely large graph. So my solutions are in quadrants 2, but I said you always have solutions in at least 2 quadrants. So what other quadrant would it be? 1. Why? Yeah, if it keeps, if you showed the top part of this, of course that would be higher than 21, but it will eventually go over into the first quadrant too.